All right, let's dive into a really cool piece of electrical engineering that honestly keeps our world from flickering into darkness, the Star-Delta starter. It's this incredibly clever trick for firing up huge motors without totally wrecking the power grid every time they turn on.
You've totally seen this, right? You turn on the AC, or maybe a big tool in the garage, and for just a second, the lights in the room dip. That little flicker? That's the exact problem we're talking about today, just on a way bigger industrial scale.
So here's how we're going to break it all down. First, we'll look at the big problem itself, that high current. Then, the slick solution, Star-Delta. We'll get into what star and delta wiring actually are, check out the hardware that makes it all happen automatically, and then wrap up with why this whole method is just so important.
Okay, so that dimming light thing, it's caused by something called inrush current. The best way to think about it is like this. Imagine trying to get a super heavy car moving from a dead stop by just flooring the gas pedal. You get this massive, inefficient roar of the engine and a huge jolt, right? Well, big electric motors do the exact same thing with electricity.
So what is it technically? Well, the second you flip that switch, the motor is just incredibly thirsty for power. It tries to gulp down this enormous amount of electricity all at once just to get its heavy guts spinning from a standstill. That brief but absolutely immense surge of power is the inrush current. And get this, we're not talking about a small little spike here. The starting current can be 6 to 8 times higher than the motor's normal everyday running current. That is a huge spike, and it's more than enough to cause serious voltage drops that can mess with everything else on the grid.
So how do you deal with a problem of brute force? Well, not with more force. You do it with some cleverness, some finesse. And that's exactly what the Star-Delta starter is. It's this time-tested, really elegant solution that manages that power surge with a kind of electrical handoff.
The whole strategy is just brilliant in its simplicity. Instead of hitting the motor with one massive jolt of power, we do it in 2 steps. It really is like starting a car in first gear, right? You get a nice, smooth, controlled takeoff, and then, once you're rolling, you shift into a higher gear for speed. So, how in the world do you create electrical gears for a motor? Well, the magic is all in how you temporarily hook up the motor's internal wiring. See, you can connect its windings in 2 different patterns. We call them star, you might also hear it called Y, and delta. And this right here is the whole ballgame. On the left, you see the star connection. By wiring it this way, we reduce the voltage going to the windings. And look at the effect. It slashes the starting current and the starting torque down to just 1/3 of what they'd normally be. That's our gentle first gear. Then, on the right, we switch over to the delta connection, which unleashes the full voltage, full current, and full torque for normal running.
Now, obviously, nobody is in there manually rewiring the motor every time it starts. This whole switch happens automatically. And the brains behind the operation are actually pretty simple. It's just 3 magnetic switches, we call them contactors, and a timer. You've got your main contactor, a star contactor, and a delta contactor.
Okay, so here's the play-by-play. The moment you hit the start button, 2 things happen at the exact same time. The main contactor closes, sending power to the system, and the star contactor closes too. That combination connects the motor in that low-power star configuration, and it starts to spin up nice and easy. And as soon as that happens, a timer starts ticking down.
So after a few seconds, usually once the motor is up to about 75 or 80% of its full speed, that timer hits 0. And this is where the handoff happens, and it's lightning fast. First, the star contactor opens up. For just a split second, the motor is coasting. Then, bam, the delta contactor slams shut, instantly reconfiguring the wiring into the full-power delta mode. And just like that, the motor is up and running at full capacity.
So let's just pull back for a second and look at the big picture here. Why do we go through all this struggle with this sequence of switches opening and closing? Why is this so critical for everything from giant factory machines to massive water pumps?
Well, the payoffs are huge. By getting rid of that massive initial jolt, you're massively reducing the mechanical stress on all the connected gears, belts, and the motor itself. You stop those big voltage sags that can mess with other sensitive equipment. You protect the motor's own windings from being fried by that intense heat from the inrush current. All of this means your equipment lasts way longer, and you're doing it with a method that's super simple, cheap, and incredibly reliable.
You know, if you only remember one thing from all this, let it be this idea. A Star-Delta starter takes a sudden, violent shove of electrical power and turns it into a controlled, gentle push. It gets the exact same job done, just without breaking everything in the process. It's a fantastic, elegant solution, for sure.
But it's not the only one out there, and that brings us to a really good question. For jobs where you need even finer control over motor speed and acceleration, when does it make sense to go beyond star-delta and look at even more advanced tech like soft starters or variable frequency drives? That's definitely something to think about. Thanks for tuning in.